All right. So when we are measuring things in the scientific laboratory, it's very, 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 very important that whenever you're measuring, you are always going to have one estimated digit. It's a little hard to read there. It's in red. It says estimate one digit. Always make sure you have one estimated digit whenever you're measuring something in a laboratory. Okay, that's very important. So, for instance, let's say I have a meter stick and I'm measuring length in meters. Well, here's a meter stick. Now, this meter stick is a little interesting. You're going to notice that it's got one big old long white area with an orange line across it. That's 1 meter. Now, if this was the meter stick I gave you, and I was like, hey, I want you to measure how long this eraser is, you would be like, less than a meter. Like, it's not a meter, it's smaller than a meter, but how much smaller is it? And that's where you have to start learning how to estimate. And why you'll understand that it's important to have more precise measuring devices, because it gives you better opportunity to be more precise with your measurements. And so I might be like, well, that kind of looks like maybe it's about 1. If I look at 10, no, maybe not quite 1. Maybe like, it's closer to 1 than it is to 2. It's closer to 1 than it is to 2. So I can only estimate 1 digit. So this is going to be 1. And it's just 1/10 of a meter. That's what I'd have to estimate that is, because it's not 2/10. It's smaller than 2, but bigger than 1. So I can't estimate 1 and 2/10. I can't do 2 digits there. I can't do, oh, that's going to be 0.15 meters, or maybe I think it's 0.14 meters, okay? I can't do those numbers because that's 2 digits bigger than what I have. It's important to estimate just 1 digit. Every time we measure in science, always estimate 1 digit between your little marks. Not 2, 1, okay? Not 0. Don't drop anything off. 1. Okay. Now, let's say I have something that's a little bit more precise. Here's my meter stick again. But now it's a little more precise, isn't it? Now it's broken down into 10 little pieces. Now, if I take my eraser, I can kind of see a little bit more. Now, I've got to measure just 1 digit. Just 1, okay? I'm going to do eraser there. Okay, so now if I start this at the end, I can see that it's definitely 1, and it's a little bit between 1 and 2. So it's got to be like 1, and maybe that's 2/10 across that little spot. Break everything up into tenths, okay? Very easy to break things in tenths. So now I can say, oh, then, that's 1 and a 2. So I can say that's 0.12 meters. I can estimate 1 digit between my measuring points. So that was my measuring point, right? Those are my measuring points. And so I can estimate that 1 digit between my measuring points. Sweet. So now I can say 0.12 meters. So before I started, and I had to say, well, it's 0.1 meters. I couldn't go any more than that because I can only estimate 1 digit. Now, for my second measurement, 0.12. Now, let me get a more precise instrument. Woo! All right, look, I've got a more precise instrument, and now I've got little centimeter marks. In fact, I actually have a little half centimeter marks as well. So now I can take that same eraser, and I can put it on there, and I can look, oh, yeah, it actually goes to 12, and it goes a little bit beyond 12. In fact, it goes to about 12 and a half. So now I can say, oh, you know what? This eraser is 0.125 meters long. Now, again, this is the same eraser, but what I'm doing is I'm using a better tool, and I can get better results. That's what measuring in science is all about. We always want to get the most precise measurement we can with the tools that we have. And so we have to always do 1 estimated digit. This time, the 1 was my estimated digit. The 2 is my estimated digit here, and the 5 is my estimated digit here. Okay? Now, I can make this measurement even more precise. Why? Because this tool has millimeter marks. And so now I can get way precise. I've always got to measure and guess the spot in between the actual lines. So let me put that thing back up there. Let me line it up. And oh my goodness, okay, I'm at the 12, and at 12.1, 12.2, and if I had better eyes, 12.35, I'm going to guess. Okay, so it's probably 0.1235 is now my more accurate measurement. Okay, And again, so you notice I'm getting more and more detailed because my instrument is more and more precise. And that's what we want to have in measuring, is we want to have greater precision. But whatever precision tool you have, however precise that tool is, you just want to make sure you're always doing one estimated digit every time. Okay? All right. So this kind of just breaks up that same kind of thing. And so you guys can kind of practice if you'd like. And you can just practice measuring at the certain points here if you want. But the idea here is I've got to estimate, excuse me, my measurement. I've got to estimate somewhere between the lines that are already there, right? This one's right on the line, it looks like. Now, if you get something that's right on the line, you need to say that. Every number that you put in a measurement is important information. And so if it's right on the line, 10 point, in this case, 3, right on the line, 0, right? Put that 0 there. That 0 is an estimated digit. I'm estimating it's right on the line. That's an important piece of information. Don't leave that information out. 10.3 is not the same as 10.30 in science. In math, it's the same. We're not in math, okay? We're in science. So 10.30 means something different than 10.3 in science. Okay, on this one, I might have said 9.67, okay? My estimated digit is a 7. In this case, my estimated digit was the 0. On this one, it looks like it's right there as well. I'm saying this is 11.30, okay? Estimated digit's the 0. J, oh my goodness, these lines, we're looking really close to being on the line. So we're just going to say 11.70. Ooh, this one, I don't know. I'm just going to go with it. It looks like it's a little bit to the left of the line. So I'm going to say 11.99. Okay. Ooh. So that's kind of how you're doing this here. You're just going through and estimating various digits. Okay. All right. You don't have to practice all those, but it's a good little thing to play with. All right. So let's define volume. Amount of space that an object takes up. Okay, it's important to keep in mind that volume and mass are not the same thing. Volume is an amount of space. Matter has volume. Mass, something that has mass will also have volume, but they are different things. Okay, so volume, the amount of space, what is it going to depend upon? Let's think about a graduated cylinder. Okay, graduated cylinder is the long, tall, okay, skinny little cylinders. And they have graduation marks on them. That's why it's called a graduated cylinder, because it's got the little marks on it. Just kind of imagine little marks on that cylinder, okay? And so that graduated cylinder is going to be something that you can measure volume in. And your unit that you measure, your base unit that you measure volume in is a liter. Now, we'll typically use milliliters in a classroom. Graduated cylinder, we would typically use milliliters to talk about that. So what is it that volume is going to depend upon? Think about the Galilean thermometer. Let me show you something real quick here. This is called a Galilean thermometer. And this thermometer is actually going to have these little balls rise and fall. Okay, it's got these little numbers on them. That one says 75, that one says 80, this one says 70. They have these little numbers on it. And these little guys, these little spheres are going to rise and fall based upon something. Okay? Volume of liquids and solids both depend upon this thing. Starts with the T. Got it yet? T-E, M. Yeah, you got it now, right? Temperature. Okay? So volume depends upon temperature. Something that is warmer is going to expand typically, and it's going to have a greater volume. Something that is cooler is going to contract, and it's going to have a smaller volume. You need to memorize this. This little fact right here. 1 cubic centimeter is equal to 1 milliliter. You will see us use milliliter over and over and over in the classroom as a volume concept. But really, it's length times 3. It's a centimeter times a centimeter times a centimeter. That's what a milliliter is. Just kind of imagine a little centimeter by a centimeter by a centimeter. Beep, beep. That's what your milliliter is. And so you should know that a milliliter volume is a derived unit from length. You take 3 lengths, you get a volume after you multiply them together. Okay? And so a cubic centimeter is equal to a milliliter. You should know that. Make sure you memorize it. Now, when I measure something in a graduated cylinder, you're going to see, here's my little graduated cylinder here, all right? Dude, look, it's a cool graduated cylinder. Yeah, well, you know, it's not great, but there it is. Now, you're going to have all these little marks on it, blah, 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 right? And you're going to have the water in it. Now, the water is going to have a little curve to it. Now, that curve is called the meniscus, okay? So when you are measuring volume of a liquid in a graduated cylinder or a beaker or something like that, then you always want to measure at the bottom of the meniscus. So you kind of look over, where's the bottom of that? And that's the place you're going to try to measure. It's kind of weird because it's in the middle and you're kind of measuring, you know, on the side where the little marks are. But that's what you want to try to do. Figure out what that bottom of that meniscus is and measure from the bottom of that, okay? That's how we measure volume in a graduated cylinder. Okay, so let's say I had a meniscus like that. What would you estimate that to be? Don't forget you need one estimated digit, right? And of course you have no numbers here, so you have no idea, right? But let's go ahead and call this a 9. We'll call this a 10. So we're at 9.5, 9.6, and I got to find the bottom of my meniscus. Where's that at? My estimated digit's got to be somewhere between the 6 and the 7. And so my estimated digit is going to be 9.6. And again, your guess is as good as mine. Well, no, mine's probably better. Oops, sorry, I'm not going to put that there. I'm going to put that here. Maybe 9.3. Was that rude? My guess is better than yours. Only because of experience, your guess might be as good as mine. 9.3 might be a little bit high. Maybe you're thinking, I think that's a 9.2. It's actually kind of interesting because you'll do the same thing like this. You'll do this in a class, and there will be things from 9.1 to 9.4. There's all sorts of people guessing all sorts of stuff on this. And so it's important to realize that you're going to get a lot of different numbers here. I think 9.2 is probably a better answer than 9.3, you know, because your 5 is probably in the middle there. And, you know, but it's a little bit of guesswork depending upon the precision of the instrument, right? That's what you guess. So everybody's got to guess an estimated digit when you're measuring. Okay, so let's look at temperature. What is temperature? Temperature is something that's going to be measured in one of these two units, Celsius or Kelvin, in our scientific laboratory. We don't use Fahrenheit in here. Use it outside, but in the scientific laboratory, you use Celsius or Kelvin. And you use a tool called a thermometer to measure temperature. You know this, right? But what it is, I don't think we really think about. It is basically the average kinetic energy of the particles in that area. So when I'm thinking about a thermometer and how it works, and think about that Galilean thermometer that I just brought there, it's actually measuring the number of collisions that are occurring on the outside of that bottle or on the outside of the thermometer, and it causes the material that's inside to expand, and that's what causes things to rise and fall. And so it's the average, okay? It's important to kind of keep that in mind, that it's the average kinetic energy of the substances. Now, typically when we're measuring temperature of a room, we're thinking about the average speed of the particles of air. That's little air particles moving around. But if you're measuring the temperature of your forehead, that's the actual speed of those particles that are inside your forehead and what they're moving like, okay? All objects have kinetic energy. They're always moving. Unless it's at absolute zero, which would be 0 Kelvin, all objects are at least vibrating to some degree, okay? Small vibrations are always moving. So temperature, average kinetic energy of a particle. All right. Now, these would be ones that you could try. These are the kind of ones that we would try in class, okay? So when you come in class, you watch this video now, come in class, we'll try this, we'll see how you're doing. But if you want to practice now to see if you're doing good, we could do things like figure out what the soccer goals, figure out about how long your bat would be in meters, things like that, okay? We'll try various different types of that. Now, remember that temperature scales are going to be different, but the like this could be a Kelvin scale and this could be a Celsius scale, and although they'll have different numbers, let's say at 0 degrees Celsius, we have 273 Kelvin, right? Although they have different numbers, at the same temperature, you would have the same expansion of that particular liquid, okay? So they look different in terms of what the numbers are, but they are acting the same. They just have different starting points, okay? All right, so then we go into mass, the amount of matter in an object, okay? Now remember, mass is different than weight. This is not weight. Weight is always affected by gravity, mass is not. So mass is going to be a constant no matter where you are, whether you're on the moon or whether you're on Earth. And we use a balance for mass, okay? Scales, we'll typically use scales here, and we can get masses, but scales are really for weight, balances are for mass. And the reason for that is because if I go up on a scale on the moon, I'm going to weigh a whole lot less than a scale here on Earth. But my mass is the same. So the scale changes, and the balance would not change. If I got onto a balance here on Earth and a balance on the moon, the balance would show me having the exact same mass. Because a balance is using a certain amount of mass balanced out with another amount of mass. So it's going to balance out my mass with another mass. But a scale is actually using a spring. And the spring is affected by forces differently. And so force of gravity is going to pull on that spring differently. And so best tool for a mass measurement is a balance. A scale we use all the time. We say, hey, go get that scale. But in accuracy, we probably want to say balance. The unit is in grams or kilograms. Okay, base unit would be kilograms. But common unit would be a gram. Think about the weight of a small little paper clip. That's 1 gram. Okay, that's how big these things are. All right, so what does mass depend upon? Does mass depend upon the location? Does it depend upon whether you're on the moon or down here on Earth? No. Does the mass depend upon the temperature? No, because the amount of temperature is going to have the same block of material taking up the same amount of mass. It's going to take up different space, but it's going to have the same mass. Its density will change, and its volume will change, but its mass will not. Okay? So think about that for a second. What else could it be that mass would be dependent upon? First of all, let's talk about that cubic centimeter. Remember that 1 cubic centimeter was 1 milliliter. I'm sure you still remember that. And you say, whoa, how many grams is that? Well, it's kind of nice and easy. 1 gram. Okay? So the density of water is 1 gram per milliliter. Very convenient. You think maybe that's kind of the way they came up with the gram? Yeah, I think so. That was kind of their standard. Now, it's not anymore. Today, they've got a crazy way of figuring out what 1 gram is equal to. But back in the beginning, when they figured out what grams were, they were like, hey, 1 gram is going to be equal to 1 cubic milliliter of water, yay, at particular temperature and pressure. Okay? One thing that mass does depend upon, if you have ever thought about or studied Einstein's theory of relativity, you know that as things speed up and get closer and closer to the speed of light, that their mass is increasing, right? Things are getting... so it does depend upon the speed that the object is traveling, based upon Einstein's theory of relativity. Time also changes with regard to speed, right? So E equals mc squared. You guys remember that? The energy is equal to the mass times the speed of light squared. So your speed is actually the thing mass is going to depend upon, which is like, what? But there you go. Okay? All right, let's go on to our next one. All right, so if we measure mass, this is what we're showing you here is a triple beam balance. We have triple beam balances that we use in class. And, basically, you've got these little chunky things that you have to move along the triple beam balance. And so let's say I move the chunk over this little piece here. And that means I've got to add 200. Move my little chunk over to this piece here. I'm now at 240. And then I have this little tiny thing that I move around. And so that little tiny thing I move around and it points right there. I would say I'm at 243 grams. Okay, you basically add the 3 different parts together to get your overall mass. And you want this thing to be wherever this thing is when the whole thing finally balances. This is a balance, then that's going to be your answer. That's how you measure mass on a triple beam balance. And hopefully we'll get a chance to do that in class. All right, so then again, we talk about weight, and weight does depend upon what? Location, that's right. Okay, it depends upon the force of gravity. And so depending upon the force of gravity, your location is going to change your weight. Okay, the amount of gravitational force on an object. So if I go up to the moon, if I'm floating in free space, those things are going to change my weight. And again, here you'll notice we are using a scale, and it is a spring scale, because most scales, you know, again, when we talk about scale, we typically are talking about a spring scale. And we use the unit newtons. Now, you might be familiar with pounds, but we actually use the newton as a measure of weight in the SI system. Okay, so I think I weigh probably close to like 200 and something, I don't know, 900 and something newtons. And so newtons are, you know, different than pounds. Okay, so again, these ones, if you want, you can pause, but we'll do these in class. Okay, that way you guys can get a chance to practice these things. So when you come to class, we'll practice some of these questions. Again, you're welcome to pause it if you want to practice on your own. Go ahead of time, but you can kind of see what we're doing there. You know, what would you measure certain things in? This is kind of a good question to think about. Like, would I measure my height in millimeters or meters? Well, you could do both, but I probably wouldn't have many, you know, things that would actually measure millimeters very accurately. And so I probably would measure millimeters or centimeters. And in fact, if you watch the Olympics, you'll see that a lot of times their height is measured in centimeters, sometimes in meters. It'll be like 1.3 meters, but a lot of times they'll do centimeters. Okay, so we would measure height in centimeters typically, okay, or maybe in meters. Personal mass. Now, again, you could do grams, but those are getting to be pretty big numbers, and so a lot of times we'll measure in kilograms. Volume of water in a cup, milliliters, right? Typical water bottle would probably have, you know, 400 or so milliliters in it. Mass of the shoe. Well, in this case, I probably don't want a kilogram. That's probably more than, that's like a heavier thing that I would need. So I'd probably measure my mass of my shoe in grams, maybe in decigrams. Room temperature, Kelvin or Celsius. Well, it kind of depends. Definitely Kelvin if you're dealing with gases and in your experiment, or we could do Celsius or centigrade. Notice that, again, the Kelvin doesn't have a degree sign on it, but the Celsius does. Okay, those are typical things that we would, typical units we would use for those measurements. Okay, so let's see how we did. Let's see what we learned in this little section here. Can we describe the steps of the scientific method? Went through them pretty fast, but you should know them. Okay, we got to start with an observation, all right? Et cetera, et cetera, et cetera. Kind of go through all those, but know those steps. Know that they're not just steps. Know that you can cycle back and have to retest, redo your hypothesis, things like that, okay? Metric prefixes, perform metric conversions. All right, so we definitely identified some metric prefixes. When you come into class, we're going to practice doing those conversions a little bit more, right? So we can show you how you might want to do like 578 meters is equal to how many kilometers, right? And we'll show you how to do those conversions. We'll do that in class, okay? Define common measurements of volume, mass, height, and temperature. Yeah, we can definitely say what those things are now. Name and use the SI units for common measurements. Okay, yeah, you can now do things like milliliters and grams and things like that. You're familiar with those now. So, good job. Okay, that basically is covering what we wanted to learn about for this section. And again, when you come into class, we'll do some more of those practices and we'll do the conversions. Just wanted to get you started with the basics there. So I hope you enjoy learning about measurements, learning about precision, estimated digits. Those are going to come up later on when we talk about significant figures, and the scientific method and how you can just kind of go through and just discover. And again, remember that scientific method, that really ties in everything, you know, in your life. Anytime you have a problem, the scientific method is there to help you kind of work your way through the problem. Make the observations, right? What is it that I know about this? Let's go do some research, okay? And, you know, so maybe it's something, you know, maybe a sickness that you have. Go do some research, figure out what you know about it. Then make like a little test, right? Okay, here are my guesses that I have this because of this. Oh, but no, I don't have this symptom, so maybe I don't have that. Okay, so I mean, you know, some of that kind of stuff, even for figuring out like, you know, what you might be sick with, the scientific method comes into play. So anyway, fun. I'm going to use it all the time, and I hope you enjoyed learning about this today.